So we're talking today about the standard error of the mean. Before we can do that, you definitely have to have some understanding what standard deviation and variance and central tendencies and all the ideas surrounding the idea of a true sample of a population. That when we do investigations, we try to get the most random sample possible that it's indicative or that parallels what the true population is. We're never going to quite get there, but hopefully we can understand the statistics enough to make the data meaningful enough for us to say, hey, maybe there's a possibility that our hypothesis is correct and we're leading in the right direction, or maybe there's a possibility that a good possibility that my hypothesis is incorrect. It starts with understanding their central tendencies. It starts with the mean. We've talked about taking a mean of the sample. We talked about hopefully that we're taking something called a normal distribution of the sample. Now, standard deviation we left off yesterday, and standard deviation is the variance, the square root of the variance. And what's so powerful about that is once we find the variance, and we did this in the previous worksheet and previous lecture, we take the variance and we square root it. And so in the last example, we got a variance of 2.5. That's basically telling us what kind of variability I have from my mean. If my mean is here, I have some spread minus and positive. Now what square rooting this variance does is gives me something called the S, the standard deviation. S squared, okay, is of course the variance. So in any case, moving forward, when we get a standard deviation, the number we get tells us something about this spread of information across a mean. And again, we're just continuing on from yesterday. And you can see that here's our normal distribution of data in this experiment. And we can see that the S, or the standard deviation, is 1.6 centimeters. And what this means is, and this is very powerful, we're able now to predict that our samples from our population will fall within 6.4 to 9.6. Now what I did there is I added the 1.6 to the 8 to get the 9.6, and I subtracted 1.6 from the 8 to get 6.4. And in this way, 68% of all the, in this case, heights fall within the normal population. We can say with confidence, with 2 standard deviation, that 95% of the entire population falls between a 4.1 height and 11.2. So what this does, the standard deviation, it gives us a variability around, or at least to be able to predict how much of these heights can exist in a population. Now that's assuming that my mean is somewhat reflective of the population that I'm measuring. Remember, this is a sample mean. This could be off. So we could have this curve dependent upon a mean that's not correct. What if I did not take a random sample? I had some bias that we talked to. This curve could be based upon something that's totally off. So we have to make sure that this mean is representative of the population, and that's what the standard error of the mean will do. It'll give us some confidence, not just the variability of data. Like remember, SD gives us what kind of variability that we could possibly have with confidence. If we're within 3 standard deviations, we can say that 99% of the population can have these variables. And of course, if you're beyond 3 standard deviations, okay, we can say that probably finding a p-plan above 12.8 or below 3.2 is less than 1% in the population. These are the extremes of the population. So this standard deviation is great. It tells us what the norms are. If you're, again, having a blood work done, and we're looking at the red blood cell count, you fall within 95% of the population by being plus or minus 2 standard deviation. All of your values for your red blood cell count could quote unquote be normal. If you're beyond 3, there's something probably wrong. You're not within the range of possibilities. That's what standard deviation gives you, the range of possibilities. Once you're beyond 3 plus or minus, then you're really outside the possible ranges, and therefore there probably is something very wrong. So it's very important, standard deviation. But again, it doesn't mean anything unless your mean, okay, is reflective of the mean that you're actually trying to measure. Meaning the mean that you get from your samples should represent the mean from the true population. So we need a value that gives us something about the reliability about this, so we can rely on this range of SD, and that is what the standard error of the mean is. Okay, so standard error of the mean is a measure of confidence about the mean. All right, so what this is it provides a measure of the spread of data from the mean. It's not a standard deviation, except it's a standard deviation of all the possible means. Let me explain. You took a mean, you averaged in from, let's say, 10 data points. In this case of this Google slide presentation, I think there was 6. It doesn't really matter, but the point being is some number of samples you use. Now, of course, the samples are always lower than the true population. So in this case, you know that the samples that you took maybe don't reflect the true mean. What if a group of people, okay, or a different researcher that was studying, let's say, the finches in the Galapagos Islands, and maybe he took 10 birds and someone else took another 15 birds, and someone else took another 10 birds. You know what I'm saying here is, what if different researchers got different samples from the true population? Let's pretend the true population is 300 birds. They couldn't get them all, but one researcher tagged 15 or 20 and looked at them, and some researcher took another 15, and someone else took another 20. As you can see, all of those 3 researchers trying to get random samples, but as you know, if there is some bias or there's some sampling error, meaning they didn't get a true random sample, the means are going to be different. So what the standard error of the mean is that if you were to take many different groupings of samples, you would get many groupings of means, meaning how good is your mean stack up to the other research, his average compared to your average? Well, the average that represents the true population is the one that has the lowest error. So what the standard error of the mean is really is nothing more than a standard deviation of all the possible means or averages that could happen by people taking different samples. So the sample means of many different samples would normally be distributed. What I mean by that is, if different researchers took the 300 birds and did different samples all over the island, they're all going to have different means, and the different averages they get by their different number of samples should be normally distributed, especially if you take a 2-bird sample, a 1-bird sample, a 3-bird sample, a 4-bird sample. Depending upon what birds you get, the average for your samples, all those individual averages by all the researchers, should give me a normally distributed curve like we've been looking at. And the standard deviation of the different averages or the means is what the standard error of the mean is. Okay, so if we look to calculate, it's very simple. The standard error of the mean tells me how accurate your mean is from your sample is likely to be of the true population mean. It gives me confidence, reliability that that value is strong, so that the standard deviation could be strong that we just talked about. So look at the value here. So the standard error of the mean, notice standard error, SE, this is how it's written in your reference table. Take the standard deviation and you divide it by the square of the sample size. Okay, the smaller the standard error of the mean, the more confidence we have. Remember, the standard of the mean is really a standard deviation of the means that could be made from different samples. So the smaller your standard error of the mean, the more confidence. Think about it this way, okay? Think about this way. If your standard of the mean is large, that means you have a lot of wiggle room. Hey, my average is 8, but my standard of the mean is plus or minus 1. What does that mean? That means that, hey, it's really an SD, right? 65% or 68%, I'm sorry, of the entire population, 68% of what you're saying is a guess, or you don't have a lot of confidence. There's wiggle room. What I mean by that is, if you have a standard of the mean that's 8, okay, that means, and it's plus or minus 1, that means from 9 to 7, that's where you wiggle, that's where you're fuzzy. So I'm confident that my error is 8. I'm sorry, my mean is 8 plus or minus 1 SEM, standard of the mean. which means I only have confidence between 9 and 7 that my error is about there. Now, if it's one standard over the mean, we're talking about the same 68% spread. So in this case that I got here that we've been using, if you look carefully, the standard of the mean, okay, the SD from the examples we were doing were 1.6. I divide by the square root of this n number, okay, so my sample number, and so my sample number is 5 from the examples we've been using, so 2.24. So all you're doing is taking your standard, your SD that you calculated from your mean, you're dividing by the square root of the sample size. And that gives you essentially the standard of the mean. So we get 0.714. Now, so this means that 68%, remember standard of the mean, it's the 1. That's really one standard deviation of your error from your mean. So that 68% of your sample falls plus or minus 0.714, which means if you had, and I forgot what the mean here is, if your mean is, I don't know, 6, you're confident your mean is representative of the true population mean between 6.714 and, I don't know, if it's 6, what's it, 5.3 something. Okay, so it tells you how much wiggle, how much you're fuzzy. If you're not fuzzy, if you're fuzzy by a little bit, you're pretty confident. If you have a big standard of the mean, you're not really that confident that your mean is far away. So let's take a look at this. Okay, the greater each sample size, and this is important, the more closely the sample mean will estimate the population mean. So as this number, take our standard deviation, divide by the square root, so the n gets bigger. As this gets bigger, the error drops. Why? Well, if you have 300 birds or finches on the Galapagos Islands, and you get all of them, well, this number is going to drop. You're going to eventually get a mean that, of course, represents the true population. It makes sense. So if we have 100 samples, my SEM is 0.16. And if with 5 samples, it's 0.714. Big difference. Larger the sample, larger the n, that drives this whole expression down. Anytime the denominator gets big, this drops. So that's important. Because we take larger sample, our sample means get closer to the true mean. Remember, standard error of the mean measures your reliability, your confidence that the mean that you got is representative of the population. Smaller its value, smaller the wiggle room, the more you have confidence. Okay, so error bars, and this is something probably brand new to you. Error bars are given to show how much confidence or how much standard error of the mean we have. This is very important. So in my example, the mean height, I guess, of the pea plants was 8. But we calculated the standard of the mean to be 0.714 and 0.714. Now this is an SEM of 1. Okay, see, it's like, so this tells me that this is how much lack of confidence I have. This is all the wiggle room. So I got 8 from my measurements. That's my average, and this is how much I'm unsure. Okay, so this is an area of uncertainty, and the bigger this bar, the more uncertainty I have. Okay, we can illustrate the SEM or standard of the mean by using error bars. So this reveals the true population mean can be anywhere from 8.7, that's just adding 8 to this value, 14, to 7.286, that's subtracting that value, just like we did with standard deviations. Okay, 68% of the time. Why 68% of the time? Because it's the first standard error of the mean. Remember, standard error of the mean is really the standard deviation of all the means that could be possible. If you have error bars with plus or minus 2 SEM, you can show 95% confidence. Okay, so this shows me that the mean can be anywhere between these two values with 68% of the time. That's not a good confidence rating. Okay, and it really isn't. If your mean can have this much variability 68% of the time, you're not very confident in this value. You need these error bars to get smaller. So let's see that. So again, one standard error of the mean is 68% of the time. Remember that standard error of the mean is the deviation of possible values of the true mean of the entire population, assuming all sample means are from a population would be normally distributed. All of our statistics are based upon a normal distribution. Okay, if you have plus or minus 2 standard error of the mean, this is what's going to give me a 95% confidence. Now this means that this is showing me how much I'm fuzzy in this area, okay? And 95% confidence is something we're going to talk a little bit more we get to chi-squared. and p-values and probabilities. We'll talk about that. So standard error of the mean plus or minus 2. People like this 95% confidence breakout point. We'll talk about that. Going further. So we have some error bars as we talked about. Now let's look at this very carefully. I've got a study between the mean length of the Crofton seedlings. Who cares what that is? Other than we measured them in the dark and the light, and the ones that were in the dark grew to a certain height, and the ones in the light grew to had light as they were germinating, had a higher standard, had a higher mean. So the question is there a significance between these means? This mean is a little like 9 point something. This mean is probably like 17 or 18. Is there a significant difference? Well, look at the error bars. I'm having a mean with this error bar, so I'm fuzzy right here. Here I'm fuzzy right here. But look at these. Error bars don't overlap. Clearly, there is a statistical difference between these two bars. I mean, these two bar graphs, right? Even though I'm fuzzy in this area, and considering how much fuzzy I'm in this area, this bar is still bigger than this bar, right? Even if I take the minimum value that I'm certain of right here and take this, what minimum value, it's definitely, we would say that there's definitely a significant difference. So if the error bars of the standard of the mean have a gap between them, that means there is some, what, very big confidence that our mean, okay, of this guy is greater than this point here. Okay, so if there's a gap between, we would say with very good confidence there's a statistical difference. Okay, so look at these two sets. Are these two sets of data significant from each other when we consider the error bars? And the answer is yes. How would the error bar affect analysis? Well, if the error bars were bigger, let's pretend I'm a princess and this was longer. If this error bar was bigger and there was overlap of the error bars, we can't say with any confidence, right? If this error bar was huge and this error bar is small, but these error bars overlap each other, you can't say with any statistical confidence that these means are different. If you're plus or minus all these values because of, let's say, random error sampling, you got a poor sample, your mean is not very close to the true population, then we can say by sampling error it wouldn't. Now, based on what they look like, because there's a gap between, we can say that there's a statistical difference, and hope you grab that. Okay, please go on to the worksheet.